Welcome to massive open online course on chemical process intensification. So, in the module 9 we are discussing something about process intensification in distillation system. So, in this lecture we will discuss something more about the distillation system. Here we will discuss the types of different distillation units based on their intensification principle, and we will discuss various types of that intensification in distillation column, even application at a different aspect. We will of course trying to have some more information on this distillation process. Now, as we already discussed that reactive distillation is one of the best success stories of process intensification technology, and it is developed since the early 1920s that made a strong positive impact in the chemical process industry, and most of the chemical industrial scale reactive distillations that will be more actually than 150 and is being operated worldwide today at capacities of 100 to 3000 kilotons per year, and it is reported by Emerson in 2007. So, this is based on that period. I think it will be more whatever he has reported. So, I can say that it will be more intensified unit based on this reactive process in the distillation column, and this actually started more than 30 years ago. He has actually reported in his paper that the intensification units, so those are developed to be more than 150. So, it may be that even more also nowadays. So, what are the different types of distillation process where reaction as well as distillation both are happening simultaneously. So, since the normal distillation column is intensified in different way, in that case we told that the reactive distillation is one of the most important distillation process where the reactive distillation even it is intensified in the next level. So, next level of the process intensification in that case would require more advanced reactive distillation configurations, and that allow an additional range of operating conditions there. So, this additional range of operating conditions actually will be incorporated in this type of reactive distillation process where intensification has been implemented. So, in the conventional system, that is called this classic reactive distillation setup, in that case that additional range of operating conditions are not available. So, for incorporating those additional range of operating conditions, even with different mechanism which are being incorporated with this classical reactive distillation process, based on which that that reactive distillation process are intensified. Now, these are some in the slides. It is shown that these are some important reactive distillation configurations where it is being developed based on that some process intensification. So, like reactive dividing wall columns, reactive cyclic distillation column, it is short form, it is called that RCYDST, that is CDIST, and reactive where internally heat integrated system are actually coming into picture, and these are also interesting in different scientific and research community, and in that case it is called as Heidig distillation column. And then another important intensification of this reactive distillation, it is called Heigy distillation, that is high gravity system, how this intensification of distillation systems are being actually incorporated. So, that is called reactive Heigy distillation. And other mechanism also sometimes incorporated to get that hybrid system of this reactive distillation system, like membrane is actually integrated with that reactive distillation column. So, in that case it is called hybrid distillation column. So, this hybrid distillation column is actually intensified based on that incorporation or adding the other mechanism for improvement of process performance in the reactive distillation column, and also reducing the cost and other reaction kinetics. Another important, it is called microwave assisted reactive distillation system. In that case, how microwave is actually being incorporated for the intensification of the process of this reactive distillation. And then ultrasound assisted reactive distillation system also are important. They are how ultrasound also can actually control the limits of the reactions there in the reactive distillation system that are being actually developed based on this ultrasound mechanism, and also it will give you that intensification of the reactive distillation process by hybridization. So, these are the different types of reactive distillation process intensification. So, we will discuss something more about that individual type of reactive distillation process where intensification is incorporated. Now, if we talk about that reactive dividing wall columns for the intensification of the reactive distillation system, it can be actually given a short form of RDWC, that is dividing wall column. So, technology is actually expanding its use of azeotropic separations and reactive distillation. So, it is reported by Kiss in 2013 in his book Advanced Distillation Technologies, Design, Control and Applications. And according to his opinion that this reactive distillation in this reactive dividing wall column system is developed in academia and applied industry, and it will give you some advantages of that integration process of this reactive distillation column for high conversion, increased the selectivity and product purity, significant energy and cost savings. So, this reactive dividing wall column, see how it is here like this distillation column, it is being divided, and this half portion of this reactive distillation column is actually configured for this pre-fractionator here, and then that in this main column there will be that reaction as well as that, and other part will be that as a separation. So, this case these are the examples. So, generally two typical configuration of this reactive dividing wall columns are applied to for the chemical engineering process intensification. This type of actually system can be used for that application to the dimethyl ether processes. So, in that case you can get that high conversion, increased selectivity and product purity, and in that case you can save that significant amount of energy and also cost. So, this is the advantage of this reactive dividing wall columns. Now, in this case a strong potential to improve that production yields to save 15 to 75% in energy uses, and also you can get over 20% in capital cost reduction as compared to the conventional processes. And in this case some limitations of course will be there, and the limitations is related to the catalyst formulation, hold up and residence time distribution, and also pressure draw, flooding, equal pressure needed in a DWC. So, for this to actually overcome those limitations in the case of catalyst formulation, hold up and other hydrodynamic characteristics, you have to do more research on this, or some research also is going on that to get remediation of this limitations based on their hydrodynamic aspects. And in this case you will see main applications are for the reversible reactions with you will see suitable boiling point characteristics there, mainly applied for methyl acetate, dimethyl ether, and fatty acid methyl esters, biodiesel production, even diethyl carbonate system also it is very important in this case. So, that is why this dividing wall column systems are important for those that reversible reactions where the suitable boiling point characteristics to be incorporated. So, in this case you can get that improvement of the production yield, and you can save some energy, you can save the capital cost also compared to that conventional processes. And in this case of course some you can say that some limitations will come based on that its hydrodynamics, because of these dividing wall systems you may get that higher pressure drop, even residence time maybe that sometimes it will be lower for these reversible reactions, and also hold up should be segregated in such way that hold up cannot be controlled sometimes that for the system. So, hold up distribution and flooding also is important there. If you divide it into a 2 parts or 3 parts, in that case maybe flooding will be more disadvantageous for that. So, you have to control those flooding formation, and also catalyst formulation is one of the important things there. Distribution of that catalyst inside the reactor, that should be one important factor to get that lower performance of the processes. So, to get that improvement of that performance of the reactions, that this type of hydrodynamic characteristics to be actually studied more, and so that you can control those hydrodynamic characteristics for having more performance of the reactions. Another important, it is called catalytic cyclic distillation process. In that case that in this process the intensification can be done based on the innovative way of fluid separations due to intensified way of thinking in contacting the liquid and vapor phases. So, in that case that unlike conventional operations, this type of distillation uses separate phases movement, and that can be achieved with technology specific internals and periodic operational mode. So, this is important for this cyclic distillation process, where catalyst cyclitization is the important phenomena there, where that the liquid and vapor phases contact will be more important driving forces for the intensification of the processes. And in that case, how that liquid and vapor phases will be distributed, based on that their movement in the momentum exchange of that liquid and vapor inside the column, based on that specific internals in the columns. So, you can get that intensification based on these internal systems. And of course, you have to operate those that CC, that is cyclic distillation, catalytic cyclic distillation, it is named as CCD. One operating cycle consists of 2 key parts there. In that case, a vapor flow period, when the thrust of the rising vapor that may prevents the liquid downflow, that is followed by a liquid flow period, when the liquid flows down the column, that dropped by gravity from one tray to the another tray below. So, this is one of the important that mode of operation by these 2 key parts. In that case, very important that there should be that 2 period of that parts, a vapor flow period and the liquid flow period. So, in the vapor flow period, you will see that the thrust of the rising vapor prevents the liquid downflow. So, in the parallel you will see that the liquid will be coming downwards. So, it will be better to get its upward. So, it can be prevented by that rising vapor, sometimes it will be prevented by the liquid downflow. And then that when the liquid flows downward, in that case dropping by gravity from one tray to the tray below, that may that hinder the rising of the vapor there inside the column. In that case, you can get the more residence time of the vapor elements there in the column. And adding a catalyst on the trays in that case leads to catalytic cyclic distillation, that is as novel process intensification approach in this reactive distillation processes. And in this case, you will see how this reactive distillation process is being happened as reported by this Kiss and Jobson in 2018 there. So, this is for here schematic of cyclic distillation internals they are, and in that case Millata trays and packings in the left side or trays with solid catalyst, you will see in the right side you will see that how these are actually taking part in this that distribution of the vapor and also liquid inside the column, and also catalyst particles how it is coming in contact with the vapor and liquid, and it depends on the distribution of the liquid throughout the column. So, this is based on that contact performance, this catalytic cyclic distillation systems are being intensified for the reactive separation process. Now, why this CCD is more important in this case? Because the internals whatever it is being used for cyclic distillation process with or without solid catalyst on the trays, this is importance there. And in that case a setup has the ability to control the amount of liquid on the tray and also thus the reaction time there. As the liquid hold up and the amount of catalyst per tray can be significantly greater than the conventional RD systems, and the applications to slower the reactions that will become feasible, thus extending the range of applicability of the RD system. So, this is one important aspects of this cyclic distillation system, but in this case there are some other challenges and limitation of course will be there. In that case that in this case you will see that moving parts especially in the presence of catalyst are there, and maybe that some obtaining good mixing is required there. In that case more research is of course to be carried out, and turbulence in the liquid phase for enhancing the reaction, but potentially damaging to the catalyst particles is one of the important shortcomings of this processes, because that high turbulence may damage that catalyst particles. It may sometimes that whatever arrangement of the catalyst particles would be made for the better contact, that may change because of this high turbulence. And also adding structured catalytic packing or catalytic internals on the tray may overcome this challenge. So, you have to structure the catalyst particles in as a packing in such a way that the high turbulence sometimes that damaging of the catalyst particles may be that overcome by this structured catalytic packing arrangement. So, that you have to think about that the how that catalytic packing can be well structured, so that even high turbulence that may not that damage that catalyst particles. So, this is one of the important challenge of getting more improvement of the catalytic cyclic distillation process for the reactions. And just as with the reactive distillation technology, you can say that this catalytic cyclic distillation process is limited to liquid phase reactions, that is to relatively low temperatures and for slow reactions there. So, in this case these are the challenges that you have to that overcome by doing and or carrying out more research on this subject. An advantage of that CCD, of course, why this CCD is coming in picture, and also how this process is being actually having more interest in the research community, even in industrial sector, that is very important, because in this case you apply the high throughput and equipment productivity for getting that more intensification process. Even high separation efficiency also can be obtained by this process, even 140 to 200% mercury efficiency as per report by that Kiss in 2018. And also you will see that you can reduce the energy requirements up to 35%, and you can also increase the quality of the products based on this process intensification of reactive distillation process in this catalytic cyclic distillation system. Another one of the important even widely used reactive distillation process, where you are operating this system with a heat input, and that heat integrated distillation column thus actually configured and developed for this reactive distillation system. In that case, heat pump assisted distillation, which uses internal heat integration, and in this case the whole rectifying section, as shown in figure here in the slides, you will see that is the heat source, and while the stripping part acts as a heat sink here. So, there are one heating sections and one other is called the stripping section. So, in the rectifying section of the column is the heat source there, while the stripping heat acts as a heat sink there. In this case, heat is transferred from the rectifying section, that is operated at high pressure, to the stripping section. So, here in this figure it is shown that this is your rectifying section, and this is heat section. Here you will see that and also you will see that stripper sections also in this figure. So, heat is going from this rectifying section to the heat section, and then it is applied to the that stripping section for the better separation there. So, this type of rectification column, or you can say the distillation column, in this case you can utilize that heat energy to get that more intensification of the processes by integration of this heat, what is actually coming out from that rectification system at its higher pressure. Combining this HYDIC with reactive distillation in a single unit, that may lead to a reactive system and with potential for the industrial applications. And this reactive system of this R-HYDIC has potential to be applied to azeotrope forming mixers as reaction that can be used for consume the azeotropes there. And in that case, some examples like tertiary amyl methyl ether production, ethyl acetate synthesis from the acetic acid. So, these are the examples where you can integrate the heat to utilize it for the better performance of the reaction, as for this azeotropic type of forming mixer, as reaction can consume the azeotropes there. And in this case, the heat whatever it is required for the evaporation in the stripping section is obtained from the rectifying section, and that reduce the heat duty of the reboiler. And primary energy savings of up to 70 to 90% as per report of KIS in 2013, and also you can save up to 22% of, that is cost as compared to the classic reactive distillation system. In this case, you remember that industrial implementation of HYDIC, it is done by that super HYDIC system by Toyo Engineering Corporation, Japan, and you can go through this website to get more details about this that this heat integrated system of that reactive distillation system. And of course, every system has some disadvantage. In this case also you may have some disadvantage of this using high integrated system of heat integrated system of this reactive system. In that case, the range of applicability it may be beneficial to the equilibrium limited reactions, and which is likely to be the narrower than that for the conventional reactive distillation system, that is close boiling mixers to avoid high pressure ratio in rectifying and stripping sections there. So, So, range of applicability is limited here, it is beneficial to equilibrium limited reactions only. So, you can do more research on this to get that wide applicability of the reaction systems where you can control that equilibrium of the reaction system. Next, another important that intensification of this reactive distillation, it is called high gravity distillation system. So, it is high-G distillation system, and in this case you will see that this technology actually replaces the usual gravitational field by a centrifugal field, that is achieved by this high gravity field in a specifically shaped rotating device. And in this case high gravity field, whatever it is maintained generally 100 to 1000 gravity, that may shift the flooding limit and allows the use of dense packing materials with a high interfacial area. So, these are the advantages of this using high gravity reactive distillation system. So, this is also one of the intensification of the process based on which you can get more performance of the reaction system in the reactive distillation column as a hybrid system. And in this case you will see that height equivalent to the theoretical plate may be within the value of 2 to 8 centimeter. In this case a volume reduction of the factor 4 to 7 for certain distillations as compared to the classic columns. Adding a catalyst to convert the system into a reactive high-G distillation, in this case it is very advantageous. You can easily incorporate this catalyst to the convert of the system into a reactive distillation. And in this case solid catalyst in the sometimes different geometric shape like wire mesh packing shows the potential of the high-G for solid catalyst gas liquid reactions and even for the reactive distillation also. In this case in 1999 Dow Chemicals successfully introduced one of the first commercial application of this RPBS, namely the reactive stripping of hypochlorous acid as per report by Cortez Garcia et al. 2017. So, this is that reactive distillation process where the Dow Chemicals they have successfully installed this that technology for the process intensification at their commercial stage by the developing is called rotating packed bed system, that is RPBS, namely for this reactive stripping of hypochlorous acid there. So, this is one of the important process intensification for getting that incorporating the packing system to get more interfacial area for the mass transfer, even for the that better efficiency of the process. But it has some shortcomings like that it may operate at high gravity that may result in erosion of the catalyst which is entrapped in the internals. And also in this case you can get the low liquid hold up and also the low residence time that may limit the application to the reactive systems with high reaction rates. And also you will see that reactive high-G technologies in this case, because of this liquid hold up distribution, even residence time distribution of that reaction limits. So, in that case you may need to do the more research on this technology to enhance the packing design and its hydrodynamics. And range of applicability is limited to liquid phase reactions only, and in that case it includes fast reactions with competing serial reactions, and also it may be that applied to achieve the enhanced selectivity and ensure the low yield losses. So, these are the some shortcomings of this high-G technology for the process intensification. Now, let us have a look of comparison of this reactive distillation processes that combined with other process intensification technologies like in terms of, if you think about the process design and simulation, that is availability of methods and tools. In that case, classic reactive distillation, of course, it is advantageous compared to the high-G technologies. Even RDWC is more advantageous than CCD, and even RD is more advantageous than CCD. Even R high DIC also is more advantageous. And you will see that process dynamics and control also, these are some that advantages and disadvantages of their level based on the availability of methods and tools. But some technologies has more that advantages than other, that is based on that different aspects like practical challenges, range of applicability, technology, readiness, even energy saving range, capital savings, all these things. But you will see that capital saving in that case compared to classic processes, you will see that RD that will be more advantageous. Even RWC also is giving advantages, even CCD also it is advantages, and high-G technology is more advantages. So, capital cost savings are more in these processes, whereas energy saving ranges will be it will be more in case of R high-D systems, where it is 50 to 90%. Whereas for RD system, that is reactive distillation system, it is giving only 15 to 80%, whereas CCD it is given 20 to 35%. But in this case RDWC, that is dividing wall column, is giving also higher energy saving range, it is 15 to 75%. But in case of readiness of the technology, you will see that reactive distillation is of course this at its commercialization stage, but for intensification of this reactive distillation stage, this is RDWC, CCD are not even in commercialization stage for as a readily used technology in the scientific community and also in industry. And range of applicability, you will see that in this case reactive distillation is more that is compared to the other geometry based intensification like RDWC, CCD, and also R high-D even for as compared to that R high-G technology. So, in all those processes, of course, that practical challenges are there, but you have to do, or scientific community, even research community, they are doing that more research on this process intensified unit of this reactive distillation system to get more advanced stage for the improvement of the process performance there. Also, you will see another that I told that if you integrate this reactive distillation by several mechanism for intensifying the process by that hybridization of this process by integrating of this other mechanism, then you can get better performance of this distillation column. So, in this case hybrid separation processes that combine two or more unit operations which contribute to a given separation task by means of different physical phenomena, like they are integrated such that synergetic effects that may allow to overcome the limitations of the individual unit operations, and membrane assisted distillation process that may constitute one possible type of a hybrid separation process. And in this case the membrane separation, a feed mixture flows over a membrane which allows some molecules to pass the membrane while others are rejected. And in the case of that membrane process, you will see that the flow passing the membrane it is called that permeate, while the rejected streams is called the retented. So, the mass transfer is generally based on the different physicochemical interactions between the components of the membrane. So, this is the basic principles of the membrane, and if we apply this membrane by integrating this unit with that distillation column, you may have that advantages like it may give you that higher capacity for your that operation, and it may be used for the flexible capacity increases due to their modular nature of that membrane, and they can easily be scaled up and integrated into the existing processes. So, these are the advantages you can get from this membrane assisted reactive distillation column. There are several that configuration of this membrane assisted distillation columns, like that configuration A, configuration B, configuration C and configuration D, as shown in figure in the slides. In this case, that in the configuration A, the feed mixer is separated until occurrence of a separation boundary, like that a low boiling azeotrope which exits as a distillate there. You see that figure in this distillation column, and how this membrane is being incorporated or integrated with this distillation column. And in this configuration A, in this configuration B, C and D. In configuration B, that you will see that configuration may consist of a membrane at the bottom. If a homogeneous catalyst containing some reactant needs to be recycled into the reactive distillation via retentant recycle. Whereas, in configuration C, you will see that it will give the high selectivity of the membrane that is used to pre-fractionate the mixture, which relieves the distillation column, and this process may lead to smaller distillation columns and lower reflux ratios. And the configuration D, you will see in that case the membrane is used to separate the 3 component mixer. So, these are the 4 different types of configurations that are being used in the reactive distillation process. And then in this case, you will see that whenever you are using these membrane assisted distillation columns, it may offers significant potential for the separation that is close boiling or azeotropic mixer type feed. And in contrast to distillation, membrane separation is not limited by vapor liquid equilibrium, and in that case this can be overcome by overcome that azeotropic and also distillation boundaries. And in that case, high selectivity, low energy consumption and a compact and modular design are further advantages of this membrane based separation. And these membrane processes are usually not economically viable if a large permeate flow rate or high purities of the both permeate and retentant systems are required. So, these are the one disadvantage of this, and also membrane assisted distillation combines the advantages of both separation principles, operates without an additional separation agent and can result in reduced energy demand, emissions and investment cost. So, this is the important aspects of or advantages of membrane assisted distillation column. You can use this membrane assisted distillation column like some application. In this case, you can say the use of pervaporation to break the low boiling methanol or methyl acetate azeotrope during the transesterification of methyl acetate with butanol. As per that report of Steengeug and Meheling that 2004, and this integrated process has also been applied to the production of cosmetic fatty acid esters, and also this pervaporation the feed is introduced to the membrane in a liquid state, and the retentant remains a liquid while the permeate is vaporized there. So, another important microwave assisted reactive distillation column is gaining in importance to the research community, academic and scientific community where this microwave system can be used for intensification of the distillation process. It can be used as an alternative source of energy supplied for the distillation process, for that esterification process, as an example you can say. And also it may use that selective energy absorption, non pollution, high energy efficiency and high production quality. You can get these type of advantages by this microwave assisted distillation system. And in this case you will see that how microwave can be utilized here, and this is your reactive distillation column, and from this source of this microwave generator, and you can apply this energy for that intensification of the process. And like synthesis of di to ethyl hexyl that phthalate, that is called DOP, that consisting 10 kilowatt microwave generator here, that is used for that intensification of the process for this synthesis of this DOP. So, in that case you can get that energy absorption efficiency, you can get that products that will be non polluted, even you can get that high energy efficiency, high product quality based on this microwave assisted column. In this case when a microwave field is applied, you will see that dielectric heating takes place that differs in the mechanism from conventional heating, and during that conventional heating highest temperatures are reached at the surface of a vessel, where bubbles can form and thus boiling occurs. This is the conventional heating system, whereas in contrast to this conventional heating system, you can apply this dielectric heating that may give you better way to get an inverted temperature gradient because of volumetric heating, whereby energy is dissipated over the whole volume by this dielectric heating system. And dielectric heating is mainly affected by two mechanisms, what is called dipolar polarism and also ionic conduction. And in this case heating is in the case of dipolar polarization, the heating is induced by the molecular friction due to the rotational motion of the polar molecules that is induced by the electric component of the microwave field. Whereas ionic conduction, in that case ionic bonding of the many refractory compounds like carbides, nitrides, always those are allows for ionic diffusion, and correspondingly you can say that under the influence of an electric field that enhance that diffusion, ionic diffusion, and hence that increase of the enhancement of the reactions, kinetics, and also you can say that more better way of or you can say that intensification way of production of byproducts by saving your energy as well as your cost. In this case the microwave irradiation can lead to the accelerated separation of one or multiple components via vaporization in the reaction system, and also it can overcome the equilibrium limitation to impel the reaction in the desired direction. An industrially relevant reaction like dimethylation reaction by microwave can prove the effect of breaking the equilibrium constraint through the elimination of gaseous byproducts by microwave heating. And in this case you can get some advantage like that by means of this microwave irradiation into the reactive distillation column, the reaction rate for a slow reaction be enhanced, and also efficiency of distillation separation can be improved, and the irreversibility associated with the distillation separation operation may be reduced by bulk heating of the microwave irradiation. Also you can achieve smaller column and also reflux ratio by specific separation process, and also you can improve the system performance, and that performance can permit further reduction in the capital investment, and therefore leads to a more compact process design, which is one of the main features of the process intensification. And also the reaction sections and separation stage would be reduced by improving you can say that reaction rate and separation efficiency. Also you can say that this research of course is required to get more intensification of this microwave based reactive distillation process, and recent research results indicate that microwave irradiation may affect the separation of the mixtures, which would lead to a more efficient distillation process, that is reported by Altman in 2010. And according to their report, they concluded that these microwaves might enhance the concentration of the low boiling components in the vapor, and also that influence the position of an azeotrope in terms of temperature and composition. So, this is the that mechanism based which you can get that intensification of the process of reactive distillation just by applying this microwaves irradiation. Another most important reactive distillation, which is very in nascent stage to get that intensification of the distillation process, that is called ultrasound assisted reactive distillation. In that case some limitations of course will be there, because this type of reactive distillation system slow reaction of course to be required for the acceleration of the reaction in order to transferable into the reactive distillation system. So, slow reactions might need to be accelerated in order to be transferable into reactive distillation. Ultrasound accelerates the reaction rates here of electrochemical, chemical and enzyme catalyst reactions, and also the combination of that ultrasound and reactive distillations, and also using of enzyme catalyst reactions that leads to synergesis which can improve the process economics in the case of high reaction rate improvement. And the possible implementation requirements of alternative energy forms as ultrasound in the reactive distillation on the basis of enzyme catalyst transesterification of ethyl butyrate is one of the important aspects of this ultrasound assisted reactive distillation. And similar to this chemically catalyzed reactions, in situ separation can also provide the benefits for the biocatalyzed reactions. And in that case by applying these enzymes in an integrated reactive distillation process, the so called enzymic reactive distillation which can overcome equilibrium limitations, and this may provide a cost advantage over the classic batch processes. And in the enzymatic reactive distillation processes, you will see that the application of this ultrasound enhance that enzymatic reactions by increasing the diffusion rates to the active sites of the enzymes or the enzymes activity itself. And the combination of this EUS, that is called ultrasound, and ERD, that is enzymatic reactive distillation, if you combine these two mechanisms to form a EUS assisted ERD, that may consequently offers the potential to the exploitation of further benefits of this process intensification of reactive distillation process. And in this case you will see you have to remember that whenever you are going to analyze this process, industrial scale ERD and the US ERD processes, you have to consider the synthesis of some specific reactions where you can get that more process intensification. Like here given one example, like if you consider the synthesis of kilotons of butyl butyrate per year with a desired purity of 99 weight percent, then you can get that this ultrasound assisted process intensification as an example. And also taking into account that significantly larger improvement of the reaction rates were reported for other enzymatic reaction system by Garrett and Rathore in 2013. And they reported that if further increases of conversions above the 50% which were experimentally determined for these systems by them would offer significant cost advantages. So, that is why it is very interesting to develop this ultrasound assisted even conjugation of this ultrasound and enzymatic reactive distillation system. You can get more process intensification of this reactive distillation process. So, we have discussed several aspects of this intensification of this reactive distillation process and what are the different improvement of the stages of that intensification for this reactive distillation system. You can have more also information about those things by further reading of these references. So, I would suggest you to go further for your better understanding, even more information about this reactive distillation system. So, thank you for your attention for this lecture today. So, next lecture onward we will try to discuss something more about that process intensification with some other mechanism and also other process intensification unit. Thank you.